Sample problem number 10. A 1,200 kilogram missile is shot straight up with a force of 20,000 newtons. You're asked to draw the free body diagram of the missile, the net force acting on the missile, the acceleration. Parts A through C are dynamics questions. Part D, however, asks for how long it would take to reach specifically an altitude of 10 kilometers. That makes this kinematics. So we again have a combined dynamics kinematics problem. In part E and F, the dynamics change. We're asked to find the acceleration of the missile now if it was shot horizontally. And we're going to assume that it flies horizontally and is not subject to wind resistance. Obviously ridiculous. And that the lift force balances out with the force of gravity. We haven't talked about lift yet, but lift is what wings produce. That's why planes have wings, is to use the air pressure for flight. Okay, so here's what we know. We know that the mass of our missile is 1,200 kilograms. FM stands for the force of the missile. It's technically the thrust, but we'll just call it FM for force of missile. And that's 20,000 newtons. In part D, notice I put a subscript Y, and that's because it's trying to reach an altitude of 10 kilometers. That means it's going up. But in X, it's covering a distance along the ground of 10 kilometers. So that's an X-axis thing. Sorry, part E, it's along the X. So we are looking to draw the free body diagram, find the net force, determine the acceleration. This is the dynamic stuff. Then we have our kinematics, finding the time, the acceleration, and the time again. This time, however, is the time it takes to rise to an altitude of 10 kilometers, where this is the time to fly that distance of 10 kilometers. Part A, the free body diagram. When the rocket is launched, the only two forces that are acting on the rocket, ignoring air resistance, of course, because that's actually a legitimate force, but this is physics la la land, and apparently there is no air resistance. FM is the force of the rocket, and force of gravity is the weight of the rocket. Some of you might be thinking, what about the normal force? That's a very good point. The normal force was there when it was sitting on the launch pad. When it was sitting on the launch pad, the ground was touching the rocket. But once you launch the rocket, it's decoupled from the surface. Therefore, the ground is no longer applicable. It's no longer in contact with the rocket. So it just fires up, and the only things that are acting on the rocket are the thrust from its engines, the force of the missile, its own weight, and if we were being honest with each other, a massive amount of friction. But the reason why we don't include the force of friction in these questions is because the force of friction due to air resistance has so many factors that affect it that it's very difficult to calculate. So we do what any good physicist does, and we just ignore the fact that it exists. So part B, let's find F net. So F net is equal to the sum of the force from the missile and its weight. And of course, dropping the vector notation, we get F net is equal to positive FM minus mg. Mg being the force of gravity, and negative because it is going down. So substituting our values in, and let's fix this. That is not N, that is M for the missile. Positive 20,000 minus 1,200 times 9.8. And that gives us a net force of positive 8,240. Now, I do want to point something out. Of the 20,000 newtons of thrust, only 8,240 newtons goes to actually accelerating the object. The balance of it was just to actually counterbalance the weight. That's why it's so expensive to send rockets into space. So much fuel is just to fight gravity. So we get a net force of 8,240 newtons up. And if we wish to be a good human, 4 sig figs. So now for part C, we're trying to find the acceleration of said rocket. Okay, so we've already derived that F net is equal to Fm minus mg. And take note, that m is not mass. It's the subscript for the missile. So make sure you make it a subscript. But we know that F net equals ma. And of course, we're isolating for the acceleration. So we must remove the factor of mass. The opposite of multiplication is division. And this is, again, danger zone. Let me clean this up a little bit here. What I'm trying to highlight is this danger here. We see a mass here, we see a mass here, and the impulse would be to try to cancel these, but you can't. And the reason why you can't is because of the subtraction symbol. This M is dividing both the FM and the mg. So since this does not have mass in it, we can't cancel like this. So if you want to do this, that is an illegal move. You cannot do that. So please bear in mind that is a common error. And I have a whole explanation as to why you can't do that. And then we've got Terry Crews reinforcing the proper algebra versus the bad algebra. Terry Crews is a national treasure as far as I'm concerned. Any case, substituting our values in now, we get an acceleration of positive 6.867 meters per second squared going up. Moving on to part D. In part D, we're looking for the amount of time it takes to rise to an altitude of 10 kilometers or 10,000 meters. Well, we know that it's accelerating, so we're going to have to make an assumption that we start from rest. Otherwise, we won't have enough kinematics information to solve. We don't know the final speed. Time is what we're looking for, and we know our acceleration. It is 6.867 meters per second squared. And again, we give it an amber check mark because it is subject to error. Since we are solving for time, we're going to look for the one equation that does not have V2 in it, and that would be equation number 2 of our accelerated motion equations, and that is d is equal to v1t plus 1/2 at squared. Mercifully, since the initial speed or velocity is 0, the first term cancels out nicely, and we don't have to worry about working with the quadratic formula. This gives us d is equal to 1/2 at squared. Well, now, since we're isolating for t, we are going to remove the following factors from the t squared. 1/2 is the same as divide by 2, and the opposite of divide by 2 is multiply by 2. And the opposite of multiply by a is divide by a. And then, of course, the final step is we need to remove the square. And the opposite of square is square root. So t is equal to 2d over a. Substituting in, we get a time of 53.97 seconds. And that's how long it would take to reach an altitude of 10 kilometers. Pretty quick. Moving on to part E. Now in part E, we have to recreate the free body diagram because the situation has changed. The rocket is now flying horizontally. So this thrust force, or the force of the missile, is along the x-axis. Now, of course, we have the force of gravity acting down. So we must have another force counterbalancing gravity as it flies, and that is the force of lift. And that's literally the wind hitting the bottom of the wings, causing it to float up. It's the same way that a kite works. So wings only work when you have an atmosphere. So again, focusing on the x-axis, we know that the acceleration is going to be in this direction here, and that's because the lift and the weight cancel each other out, and that's where we get over here. This is why we can avoid working with F net X and F net Y. The Y component just cancels out. All right, well, replacing F net with MA, and we know that the missile is going in the forward direction, making it positive FM. Isolating for acceleration, the opposite of multiplication, of course, is division. So we get 20,000 divided by 1,200, and we have a significant increase in the acceleration. And that's because we're no longer fighting gravity. Of course, in real life, there would be air resistance, and that rate of acceleration would not be that high as a result of it. But again, physics la la land. Part F, we're looking for the amount of time it takes to reach a distance of 10 kilometers or 10,000 meters. Again, we have to have a necessary assumption that the initial velocity in the x-axis is 0 meters per second. Rocket starting from rest, basically. We have no idea what the V2 is, and we don't need it because we have enough information. We have our dx, our vx1, our ax, and we're looking for our time. And quite conveniently, it's the same formula that we used in part 2. In part D, I should say, because in part D, we had the same kind of information. Well, we already went through all this step in part D, so I'm just going to recycle this equation number 2, substitute our values in, and we get 34.64 seconds, about half the time to reach that distance than it did to reach the altitude of 10 kilometers. And just to give you context of how far 10 kilometers is, 10 kilometers is approximately the distance between Masonville Mall and Victoria Hospital in the south end of the city. Pretty impressive to cover that in 34 seconds.